we've thought about circular motion kinematics in a magnetic field, so now let's do a problem. So this is going to be, if you're using Serway and Jewett 8th edition, this is chapter 29, problem 22. And if you're not, don't worry about it because I'm going to tell you the problem anyway, so it doesn't matter. Okay, so in this problem, we have a region with a uniform magnetic field pointing into the board. So this is, remember how we always draw a field into the board like this. But the uniform field does not exist everywhere. It's only to this side, say, of this dashed line. So on a plane to the right, you've got a magnetic field pointing into the board, and to the left, the magnetic field is 0. Here, we're going to give it a value of 1 millitesla. The magnitude is 1 millitesla. Here, the magnitude is 0. Okay. So now, an electron is going to fly with an initial velocity, and it's going to hit this uniform region perpendicular. So it's flying perpendicular to this boundary of the board. And you know what's going to happen is when it goes into the magnetic field with some velocity, it's going to make a circular orbit. And you can kind of imagine it's going to come in, it's going to make a circle, and it's going to go out. So that's really the problem. So we're given the electron has an initial velocity, so we'll draw it here. Electron, initial velocity, and we're just given v. We're given numerically 1 millitesla for the field, but we're only given v for the velocity, or whatever. So let's say it's going to come in, enter the region of the field. Let's calculate the force. It's going to be v, fingers along v, right-hand rule, cross with b. The force is going to be up. No, it's not going to be up. It's an electron. The charge of the electron is minus e. So when you put that in, the force is going to be down. So I drew this on the wrong side on purpose, of course. So I'm going to draw this up at the top. Because since the force is down, here's your electron, has an initial velocity v. It's going to go in here. And yes, Q, let's see, v cross b would give you the force up. But since the electron charge is negative, flips the sign. The force is down. So since the force is down and the velocity is this way, it makes a semicircular path like that. And it comes out as an electron with that same velocity v once it gets out. So that's what we're given. Electron, velocity v, goes into 1 millitesla. The first question is A, how much time does it spend in the B field region, or just the B field? Basically, how long does this take? It looks like a tricky problem because we were given 1 millitesla, but we weren't given the velocity. We don't know how fast it's going, and we don't even know the radius. The radius would tell us how far it went. So how do you do kinematics? Well, when you know what to do, you just start writing down the equations that you know, right? So the radius, we know if we're in circular motion, we know that that radius is mv over qb. Okay, well, we don't know v, so that doesn't get us very far. But the other thing we know is that omega, the frequency, is qb over m. And this is the one that's going to help us, because remember, for the frequency around which the particle goes around a circle when it's going in just a circular motion, all it depends on is the magnitude of the magnetic field and the properties of the particle. The particle's mass, which we know because it's an electron, and the particle's charge, which we know because it's an electron. This is actually the one that we know. And omega is really what we want. Remember, omega is the angular frequency. How fast is it, how often does it go around? That's really the question. How long does it take to make this semicircle? So we don't really need to do the kinematics in terms of d equals vt. We really just need omega. So let's think about what omega is. This is a check mark, by the way. There you go. It's less confusing. Let's think about omega. What was omega? Omega is the grown-up physicist way to think about frequency, right? Omega is in radians per second. Now, we're used to thinking of frequency possibly in terms of hertz, in terms of f, cycles per second. Right? So remember, this is how you tell them apart. F is in cycles per second, or hertz. But remember, a cycle, when you're going in a circle, is 2 pi radians, right? Cycles per second, it's cycles per second, sort of. So if we're going this many cycles per second and we're talking about circular motion, if you want to get it to radians, you just say, well, how many radians are in a circle? Well, 2 pi. Right? That's how you get from omega from F, what you're used to thinking about. Okay. F is related, the frequency is related to the number we need. We want to know how long does it take to go around the circle? Well, that's the period. That's what you know is the period. So we know that's 2 pi 1 over t, where big T is the period, and that's just in seconds. Okay. And we know this all is equal to QB over M. So if we wanted to solve it for just the period, then you would just turn this whole thing around, and what would it be? T would be, this would come over here, it would be 2 pi M over QB. That's how you get the period. So let's go ahead and start plugging in numbers, see what we get. Let's see, T, the period, is 2 pi. We know what those are. The mass is 9.1 times 10 to the minus 31 kilograms. And the charge is 1.6 times 10 to the minus 19 coulombs. And B was a millitesla. That's 10 to the minus 3 teslas. So if we do everything in MKS units, that's what we get, and therefore the answer is going to come out in seconds, but I'm going to put nanoseconds. It comes out to 36 nanoseconds. That's not the answer. Right? That's the time it takes to go all the way around the circle. But our path is only halfway around the circle, because once we go halfway around, we come out of the field. Okay? So the real answer then that we want is simply half of that, 18 nanoseconds. So the electron flies in, doesn't matter what its initial velocity is. It can be going really fast or really slow. It's going to go through here in 18 nanoseconds. All that matters is the properties of the electron and the magnetic field. If it's going really slow, then it'll just do that. If it's going really fast, it'll make a bigger circle, but it'll always take 18 nanoseconds.